Hello again, everyone. So let's continue our our section on basis of architecture and machine programming. First, let's start with the definition. So, what is architecture? Well, architecture, which is the same thing as instruction set architecture, are the parts of the processor design that one needs to understand to write assembly code. Okay, remember, it's the hardware-software interface. Really, it's the hardware-software interface. And another way of thinking about it, it's what's directly visible to software. If it's visible to software, it means that you have to know about it when writing code. Okay. Now, the microarchitecture, on the other hand, are details of how the architecture is implemented. Essentially, it's more details of how the instruction set architecture is implemented. Okay. So let's just think through some examples here. So, as we saw briefly, we're going to see more detail later in the course. A cache is a very fast piece of memory that lies inside the processor that happens to hold recently accessed data. Okay, so now is cache size architecture? Well, it's not directly visible to software. That means that it's not part of it. It's used by software, but it's not directly visible. The size is not directly visible, so it's not part of the architecture. How about core frequency? Well, core frequency is also not something that software knows explicitly. Software doesn't care all that much about what the CPU frequency is. The user does because it makes the processor faster. But when writing assembly code, you don't know, and there's nothing in the ISA that refers to that. So this is also what's core frequency? Core frequency is part of the micro architecture or the implementation. Okay. So, and the number of registers, well, number of registers is something that you need to know because you're going to use registers explicitly in your assembly code. So, number of registers is part of the ISA, therefore is really part of the architecture. Okay? So now, with that in mind, let's look at the assembly programmer's view of your system. Okay? Here we have the CPU, the central processing units, and there's three important things that an assembly programmer needs to know. First, there's a special register called the program counter. Okay? The program counter holds an address. It holds the address of the instruction that's going to execute next. Okay? Remember that a computer executes one instruction after the other. And the program counter tells which instruction is going to be executed next. Okay? By the way, it's also called EIP in IA32, and IP stands for instruction pointer, and E is called extended instruction pointer. And now in RIP, IP in this case also means instruction pointer in x86 64. Okay, this is just names for the program counter. Now there's also a bunch of registers that are just used by the assembly code directly. And by the way, these registers to hold data, essentially a piece of very fast memory that is addressed explicitly by your assembly code. Okay, and now we also have condition codes. In condition codes, it's essentially tells you the result of the status of some operations that was just executed by the instructions. For example, it tells you whether or not there was an overflow. Okay. It also tells you when you do a comparison, say you want to compare whether a certain register holds a lower value than another register, the result of this comparison is set as a condition code. Okay. So now, now on this side here, we have memory. And memory, well, memory is meant to hold data and code. Okay, that includes the operating system as well. And also, there's a piece of data, special data structure called the stack, which we're going to see later in the class. It's very important for program execution. But now the bottom line here is that the way it works here, we have the CPU, and here we have memory. The CPU sends addresses to memory when it wants to read data into registers, and the memory gets data, sends data back to the CPU that puts it in registers, okay, or does an operation with it. Now, the CPU also can send data to memory. It can get data from registers and say like, hey, memory, store this data for me. Okay? Now, another thing that's very important is that instructions themselves, like object code, also known as object code, comes from memory. It's stored in memory. So that means that the processor has to fetch these instructions from memory in order to execute them. Okay? And memory is just an array of bytes that has, and each byte has an address, essentially a table, very large table of bytes where you can address them directly. Okay, So now let's look at how we turn C code, high-level C code, into object code, okay, into machine code. So here are the steps. So in this example here, we have, you know, two source code files. This is .c files that holds code or text written in the C language. Okay. Now you're going to use a compiler. GCC is just a popular open source compiler that we're going to use in this class, and it's used by a number of people. And what this compiler is doing is it's just taking two C files as input. It's going to compile them and produce a single object file. That's what the minus O is doing here. Okay, so that's the output, producing a P binary file P that holds the resulting machine code from the source code. Okay. So now, going these steps here, we start with what we call the text. That's the text of your program, the source code. You run through a compiler, okay? And if you use the -s option, okay, so you're going to produce .s files that hold the assembly code generated by the compiler, okay? Now, you're going to use the assembler. We saw this before. The assembler takes assembly code and produces binary or machine code. Okay, and what it's doing here is so getting this in this example here, getting the P1.s and P2.s and translating them into binary machine code equivalent to the input assembly code. Okay, so and then the final step is there's something called the linker. That what it does, it gets the object code that has some symbolic names in them and links with libraries. And what are libraries? Libraries is essentially a collection of precompiled code that's available for use in user code. For example, things like to print values on the screen, to access operating system services, and so on. This all resides in libraries. And the linker gets together the object program, links it with the libraries, and produces a final executable program. That's what you can type and run in the command prompt. Okay. And in this case here, we're also using an optimization. This -01 here is just telling the compiler, hey, apply some optimizations to our code when generating it. Okay. So let's see one example of a translation from C to assembly. Here we have in our C code a very simple function, sum, that takes two integers as input, perform x and y, adds them, puts in a variable called t, and then returns t. Okay, so that means when you execute sum and you pass the parameter, it's going to return the sum of those two values. And sum is the name of the function. And now in our generated assembly code, what we have here, we have the name of the function and colon, saying that the function starts there. And we're going to see this in detail more, but you know, these instructions here move data between two. This instruction is moving data between two registers. This one is reading data from memory. More specifically, it's reading on one of the parameters. And this is where we're actually doing the addition with the other parameter, and now we are producing the result. And this return instruction here just returns from the execution of your function. Okay, it goes back to the caller of the function. Okay? And the way you would obtain this, I mentioned this briefly before, is you can go to compiler. -s tells the compiler to produce assembly code. When you give a .c file, it's going to produce an equivalent file that's now .s that holds the assembly code. Great. So now there's three basic kinds of assembly instructions. Okay, there are instructions that perform arithmetic, things like addition, subtractions, and so on, both on register data as well as memory data. And there's one type of, the other type of instructions are instructions that move data between memory and the register. You could say you could load data from memory into a register. Okay. There's also instructions that get data from a register and stores it into memory. Okay, that's the second category. So transfer between data transfer between memory and registers. And finally, the third basic category of instructions is ones that transfer control. And control here means what instruction is being executed at any given time. So the flow of control is the flow of instructions that are being executed. Okay, and it means when you do a jump, essentially jump, you're executing your program here. Okay, so suddenly you can just jump at a different part of your program, and you can jump back and continue executing. Okay. So, and this is very useful because when you have something like an if in your program, if something, that's actually making a decision of whether or not you should jump to a different part of your code. Okay, so with that in mind, now that we know the basic types of instructions, let's look at the basic data types in assembly. So now for assembly, you essentially have words, you have units of data that it would be 1, 2, or 4 bytes in the case of A32, or also 8 bytes in the 64 in the 64-bit ISA case. Okay, so in this integer data holds both data values, like really program data in the form of integers, as well as addresses. And note that data in assembly is essentially untyped. Okay, so so that means that a register could hold an integer of a certain width, or it could also hold a register. The register doesn't really know. It depends on how you use it. That's going to determine what it's going to be seen as an address or as a data value. So the other data type, most ISAs today support floating point operations in the ISA. So that means that now floating point data is held in special registers in the processor. It means that implicitly there is a data type. You know, there's a floating point is a data type that is that a programmer writing assembly code has to be aware of. And now, what about aggregate data types? Aggregate data types in assembly. Is there such a thing? No. In fact, for assembly, everything is just a contiguously. It's memory is flat, and there's no notion of arrays. You have to implement it by hand, by laying out the data in memory properly, and then accessing it in a way that makes it look like an array. Okay. So we talked about object code before. Remember that the assembler translates assembly code into object code, binary code. And here's an example. Like, remember the sum function that we just saw that adds 2 numbers? Well, these are the bytes that compose the machine code for the sum function. Okay, this happens to be a total of 13 bytes, and there's a bunch of instructions encoded there. You know, some instructions take only 1 byte, some other instructions take 2 bytes, other takes 3 bytes, and so on. And this is also saying that where the code is located in memory starts at address at this address here. Okay, that's right. This is where it starts, and this is also saying that's the address of the first byte here of this function. Okay, so and as you see, it's actually not obvious where instructions start and end because they have different sizes, and you have to decode them in order to understand what they do. Okay, so now I mentioned this before briefly, that what the linker does essentially is it resolves some symbolic names that are embedded into the object code, and also links what's missing. Like if your code happens to use some system library functions like malloc to allocate memory or print stuff on the screen, this has to be linked. You know, your code has to point to the right place in these libraries. All right, so let me show you an example of a machine instruction here again. So remember that in our sum function, we had this statement here, int t equals x plus y, which just adds x and y and puts it into variable t. Well, there's an add here, so it's only natural that in our assembly code, there'll be something that looks like an add. And that's the instructions emitted by the compiler to implement that, that expression. Okay, so the C code here, what we're trying to do is add 2 integers. And then in assembly code, what we're doing is we're adding 2 4-byte integers. Okay, so and by the way, note that it's the same instruction whether it's signed or unsigned. Okay, so Gaetano told you about signed and unsigned integers, right? So you know about that now, but the instruction doesn't know whether it's adding a signed number or not. So now so here are the operands of our operation. So we're doing this addition here. Right, x plus y. Now x has to be somewhere, and in this case, it happens to be stored in a register called EAX. That's one of the registers offered in the x86 ISA, and that's why it's one of the parameters in this function here. Sorry, in this instruction. So now y, the variable y here, happens to be located in memory. Okay, so it's located in the memory that is represented by the contents of register EBP, which is the base point, the stack base pointer, plus 8. So what's going to do is this, using this expression, you're telling the processor that, okay, one of the other operands in this addition happens to be stored in memory, and it's 8 bytes away from the address contained in the register, in register EBP. Great, okay, so now in T here, which is where the result of our addition goes also happens to be a register, which is EAX. So in fact, EAX is both an operand as well as the destination of the operation. Okay. So and now, okay, this instruction here, that's the assembly instruction, and it became 3 bytes in our object code, in our machine code, and it happens to be stored in this address here. Great. All right. So now, as you saw, it's very hard to tell from machine code unless you really can keep your attention, do everything in your head. It's just very hard to disassemble the code in your mind, to look at the bytes that correspond to your binary code and think about what instructions they do. That's why there's this process called disassembling. What disassembling does is it gets the bits, the bits from your machine code and maps them back to the original assembly code. Okay. So if you remember before, I showed you the bytes that composed the sum function, and here are all the bytes, all the 13 bytes here. And then this first byte here, 55, just happens to map into this instruction called push that pushes something to the stack. Okay? And now these 2 bytes here in my machine code happens to map to this move instruction that moves data between 2 registers. Okay? So the way you do this, by the way, there's this tool, this utility in your Linux installation called obj dump. It dumps the object. It gets the object and dumps its disassembled assembly into the screen so you can see. Okay, so it's very useful for you to examine code, and I encourage you to run this command man1 obj dump. That's going to tell you how to use this tool. Okay. So, okay. Now, here's another way. This is just a different way of looking at the disassembly. It's just a different formatting. And now it's showing that all of the addresses now are just relative to sum. That's where sum starts. So you can see that this one is 1 byte away from sum, and so on. Okay. And this is what you get if you did disassembly with the GDB debugger. Okay. Great. So what can be disassembled? Well, anything that can be treated, that can be interpreted as executable code can be disassembled. Okay, so you might try to get any random piece of binary data and disassemble it to disassemble it. You might not get valid instructions. Okay, so what makes sense to disassemble is essentially parts of your memory, right, that happen to store really binary code. Okay, so essentially anything that can be interpreted as executable code can be disassembled. Okay, so now I know I've already mentioned registers before, but I just want to spend a little bit of time saying what is a register. So a register is just a location in the CPU that stores small amount of data. In fact, one of the reasons that registers are so fast is because they're small. Speed of light is limited, right? So if the speed of light is limited, you make it small, it means you can make it very, if things are small, you can make it very, very fast. Okay. So in register are just very fast locations, but they're very small that happen to be inside the processor. And as we're going to do some assembly program, we'll see that registers just appear everywhere. And they happen to be really precious because we only have a handful of them, especially in x86. So let's see why. Okay, so we have IA32 has 8 registers. Okay, have 6 registers that are called general purpose, that can hold any data you want. And there's like 2 special purpose registers. One that holds this pointer to the stack, and one that holds the pointer to the base of the stack. Okay, so here's, so the origin is mostly obsolete, but the way to think about this is that this used to be called EAX because it's supposed to be accumulate, and a lot of instructions does accumulate to EAX. But you don't have to use it like this. It's just mostly what was the intention, but you can really use them anyway. Except for the stack pointer and the base pointer, they really have special meaning. Okay, and you use them as they were intended. Now, so in IA32, right, these registers here are what? 4 bytes wide. They're 32 bits wide. Okay, so now but that's not that doesn't mean it can only access all 4 bytes at a time. There's some alias to the register. If you use just %AX, what are you referring to is only this part of your EAX register. And even more, you can reference only a specific byte. If you use this name in your assembly code, %AH, you're just referring to this byte of the EAX registers. And the same thing for the other registers as well. Okay, except that for these registers you can only access half word or half register. So now let's see how x86-64 registers look like. Well, not surprisingly, now again what happened was you have EAX here, which is and then in the other IA32 registers are also available, but they're now only part of larger registers, because these here are for example, IRX happens to be what, 64 bits. Okay, and this one here inside is 32 bits. Okay, and the same thing for the other ones. Now the nice thing about this is that you preserve backwards compatibility. Isn't that great? So now you just happen to you have the same names, and then now since registers are bigger, now they have to be a superset of the original ones. Okay, so but RA6, it doesn't end there. x86-64 also give you extra registers. Okay, so now we have all these other registers here for general purpose use that can also be used by your assembly code. Great. So to summarize and end this section, we saw what is the instruction set architecture. It defines the system state and all the instructions that are available to software. We talked a little bit about the history of Intel processors and AMD as well. And we looked at how C relates to assembly and machine code. We gave some initial examples. And we talked about x86 registers, which is really at the heart of assembly programming in x86. And the thing I want you to remember is that they have a very, very limited number, and some of them have special meaning. So not all of them are general purpose. Okay? Thank you. So now this concludes our section. Now we're going to see next section. We're going to start looking at the specifics of how to write x86 assembly code. Thank you, and see you soon.